In this video, we're going to introduce quantum mechanics. Quantum mechanics is a field of physics that has to deal with the movement and location of subatomic particles. Before we get there, we're going to talk about the de Broglie relationship. And the de Broglie relationship basically looks at the fact that if light can act both as a wave and a particle, can the opposite be said then of something we think of traditionally a particle? And by that we mean anything from the size from a baseball, football, the Earth, to electrons. And so the de Broglie relation basically assigns a wavelength to objects we think of as being solid and that type of thing. And this is the formula here. So the wavelength is the Planck's constant. That's still 6.63 times 10 to the minus 34th. The mass in kilograms of the object, and then the velocity in meters per second. So here's a problem here. Okay. And it wants to know what is the de Broglie relationship, or de Broglie wavelength for an electron moving at 2.42 times 10 to the 6 meters per second. So we want to know what the wavelength is. The meters per second is a unit of velocity, so my velocity is 2.42 times 10 to the 6th. And I would give this to you that the mass of the electron is, so my mass is 9.109 times 10 to the minus 31 kilograms. So the formula is wavelength is h over mv. Again, h being Planck's constant is 6.63. Times 10 to the negative 34th. That is a 4. So the wavelength is 6.63 times 10 to the negative 34 divided by the mass of 9.109 times 10 to the minus 31 and divided by 2.42 times 10 to the 6th. So when I enter this, I want to enter 6.63 times 10 to the minus 34th, or e to the minus 34th, divided by 9.109 e to the minus 31, divided by 2.42 times 10 to the 6th. So again, I would make sure, pause your calculator, pause your video, and make sure that you can enter this into the calculator correctly. And when you do that, you get 3.01 times 10 to the minus 10th, and the units is meters. And visible light is 4.0 times 10 to the minus 7th to about 7.0 times 10 to the minus 7th meters. So this is below visible light, probably down in the UV range. Okay. Here's another example of something much bigger than an electron. Albert is a cat. And what is his wavelength when he runs to his food bowl? So again, it wants to know what the wavelength is h over, wants to know what the wavelength is. Okay, and I have a mass of 5,200 grams and have a velocity of 1.6 meters per second. So again, the formula is wavelength is Planck's constant over mass and velocity. Planck's constant is 6.63 times 10 to the minus 34. So the wavelength is 6.63 times 10 to the negative 34. Divided by my mass has to be in kilograms, so this is 5.20 kilograms. Move it 3 to the left, 1, 2, 3. All right, so 5.20. My velocity of 1.6. Again, it's this 6.63 times 10 to the minus 34th divided by 5.2 divided by 1.6. And when I do that, I get 7.97 times 10 to the negative 35 meters, so that's very, very tiny. Okay. Now, the two problems I did here were to find the wavelength. It is, however, reasonable that you could ask to be found the mass, I can't speak, mass, and the velocity. So you could also have to solve for either one of those if you're given to wavelength. All right, the next thing is what I introduced before at the beginning, which is quantum mechanics. It's basically, like I said, it's the branch of physics that deals with the wave properties of submicroscopic particles. Of course, we're dealing with electrons, so we're going to be focusing on that part. And Heisenberg, which doesn't have the name anymore associated with it, I don't know who he made mad in the science field, but he no longer gets his name associated with it. Heisenberg's uncertainty principle says that you can neither know both the speed and position simultaneously. So if I know the position, I don't know what the speed is, or the momentum. If I know the momentum, I no longer know what the position is. And so basically by trying to measure one, I disturb the other. And so you can either know the position or the momentum accurately, but not simultaneously. Okay, so you can't know them at the same time. And I think about this as basically, if you think about having a bowl of water or a bucket of water, and you have a leaf floating in there, a small piece of leaf, okay, like a speck of dust or something. If you go to get it out and you miss and you don't hit it straight on, then it moves away from your finger. And that's kind of the same thing. By probing these two items here, I cause it to change where it's going. All right? And so what we can do instead is predict the probability, and that's what quantum mechanics does, is it has formulas that predict the probability of where you're likely to find an electron position. And so atomic orbitals is that wave function. It's a mathematical function of finding it. And so these letters may look familiar to you, S, P, and D. Okay, in the next chapter we're going to get into electron configurations, and these are the fact of letters that you use for electron configurations. S is spherical. Okay, so if you have an electron in an S orbital, then it's going to be inside a sphere. If you have an electron inside a P orbital, there's 3 orbitals here, X, Y, and Z, and they basically look like dumbbells. I like the images in which it looks like 2 tied balloons together, where you tie the knots together. And then it's along the x-axis, the y-axis, and the z-axis. These are the D atomic orbitals. They get a little bit more complex. They have 4 lobes for 4 of them, and they're just on different axes here. And then you have this odd one, which is a ring with a dumbbell through it. And so there are 5 of those orbitals there. And that is the end of this section.